Ladies and gentlemen, in this section we will discuss and understand all about diffraction. To do so, we put together the following issues. First of all, we shall take a look at the single slit diffraction. Then we will derive Kirchhoff's diffraction formula. We will learn about the different approximations in the midfield and the far field. We will learn about circular apertures and diffraction regimes. This will be very interesting to see. We will learn that there are three main regimes in diffraction. As an example, we will take a look at optical resolution and as an outlook on the diffraction of a Gaussian beam. So in more detail, we will start with an animation which you soon will see. It shows you what happens if we have a plane wave approaching a slit, and then we look at what happens directly after the slit with the transmitted light. In the very vicinity of the slit you will see a shadow. It will be just a shadow effect, but further down you already see here some interference patterns, and in the ultimate limit of the large distances, again rather more simple distribution of the light. In the right-hand picture you can see the corresponding cross-section through this interference pattern according to the position in distance from the aperture. So if we start this movie, you see now in the beginning we have very many interference maxima and minima. Further down this number reduces, and ultimately in the end, approaching large distances, we get a more simplified distribution with a peak in the center, and in the limit of infinity you will see a very simple distribution. It is a Fresnel far field distribution, a sine square over x function, which is called a sinc function, which you may know from Fraunhofer diffraction already. Well, to look at it in more detail, you see here displayed at several positions the corresponding distributions of the intensity. So very close to the slit, at a distance 0, we have a rectangular shadow distribution. Not too far from the slit, it is looking quite similar. However, we already have individual maxima and minima and so on. Going further down, it simplifies, as I said, in the end towards this sinc function. Well, in this context, it is physically meaningful to define a magnitude called the Fresnel number. The Fresnel number is a dimensionless number, which is just the area of the diffracting surface here. So it's in a rectangular aperture, just the dimension squared divided by the wavelengths of the incident light and the distance from the aperture, from the slit. So you immediately see for small numbers of z, which is distance, the Fresnel number will be very large. In the limit at the slit z equals 0, the Fresnel number will approach infinity. So the physical interpretation of the Fresnel number is the number of maxima we can count at the special position on the optical axis, increasing the distance to the slit. And that works inversely with the distance. So here we have Fresnel number infinity. Then the number of maxima gets smaller and smaller and smaller until we only have one left in the limit of infinity. How does that work? If we look in more detail at what happens at the slit, if we approach the slit with a plane wave, we can use Huygens principle to explain the interference patterns. Huygens principle says that each point at a wavefront can be interpreted as origin of a spherical new wave. So in the limit you can see already that if we superimpose all of these individual sources, we get a line, a linear wavefront reproducing itself. However, at the edges after the slit, you already see that we have radial parts, And now the next step is that at a certain point, given distance z from the slit, somewhere in the volume of consideration, we now can add up the intensities coming from each of these individual spherical waves from the slit. So you see, as a result, we get an integral in summing up all contributions from these individual point spherical waves in the slit at a certain point E of x, and E of x is the electrical field strength at that point, which of course is a superposition of all contributions along the individual sources on this slit. And that shows this integral here. Here you see the radial waves and their participation. We integrate it over x prime and y prime, the position, and we count and add up all the contributions of the individual point sources by these two integrals over x and y in a thought two-dimensional diffracting aperture. So this is actually the integral, the diffraction integral, the diffraction formula developed by Kirchhoff. Physically pretty simple by just adding up all the contributions of the individual spherical waves. We then have to allow for what is called an inclination factor. It scales with the cosine of that angle of diffraction. Needless to say that at large angles, in the limit 90 degrees, we will have no contribution, and that's why the cosine works very good as a damping function, so to say, for the relative intensities independence of the diffracting angle. In this slide, we formulated a more general appearance of the Kirchhoff diffraction formula, which is a general solution of the Helmholtz equation, the wave equation, as you can see it here. And it holds for a more general case in which the sources are distributed in an arbitrary volume. So in our special example, this volume actually consists only of a straight line which represents the area of diffraction. But in this general case, we have contributions from an arbitrary volume all over the place to some screen which also may be placed inside that volume. To come back to our special case with the diffracting aperture, we now make a further simplification. That is something you may remember from earlier lectures, the so-called slow varying envelope or large distance small angle approximation. If we look at the expression in the Fresnel formula, we see the dependence on x and y, and now we can develop this root which ultimately represents the radius, and if we do so, we can neglect higher order terms because the angles under consideration are relatively small, so we can neglect x and y coordinates with respect to L. And then the result is the Fresnel formula as you can see it down here. Again, it is an integral summing up all the contributions of the individual light sources to this final value of the electric field at the point of consideration. So far, we learned about the physical background, the content and the interpretation of Kirchhoff's diffraction formula, and we derived it from a very general starting point, the Helmholtz equation, and came to the general formulation of this diffraction law. In the following, we will look at approximations in the far field and then take a look at some practical consequences of this diffraction formulation. So in this first approximation, we look at the Fraunhofer approximation, which is the far field approximation of this diffraction solution. So what we do is we let the distance of consideration go to infinity, and so one of the terms in the integral vanishes and the solution for the electrical field simplifies to this expression here. And this formula states the far-field distribution, and it is actually mathematically pretty straightforward and simple because it is directly proportional to the Fourier transform of the near-field distribution. In this case, we already see the clear correlation of the far field and the very near field in the vicinity of the diffraction pattern. As a result, we obtain in the far field the distribution you saw in the very beginning already. So this is the sine square behavior. In this case, you cannot recognize a sine square because now we have radial symmetry in the coordinates, and then the solution is a Jink function, which is very similar to the sinc function, however represents the spherical nature of the diffraction pattern. So, in order to summarize what we have learned so far, you again see here a display of the downstream behavior of the diffraction patterns, and you remember there is a Fresnel number which is defined the area of the diffracting surface divided by the product of lambda and the distance to this diffracting element, and we have one area which we call the geometrical area. Geometrical optics are valid. We have shadows, very simple solutions. This is when the Fresnel numbers NF are very, very large, in the limit at the aperture itself, infinity. If we go to the very limit of large distances, again the solution becomes analytically easy to calculate. It is the Fraunhofer diffraction, the Fourier transform of the distribution at the diffraction point. This is for Fresnel numbers around or smaller than 1. And in the intermediate part we have what we call the Fresnel diffraction, which unfortunately needs solution, individual solution of this rather complex equation, and we cannot make a simple approximation in this case. Again, the example of focusing a rectangular beam distribution with a lens to a focus, we observe the very same interference pattern as we observe it in the limit of infinite distance from a diffracting surface. That is this Bessel function, this Airy disk, which we can see also directly in the focus. So in the focus of a lens we have the conditions exactly the same as in the limit of infinite distances of a diffraction aperture. And it is a Bessel function with a 0 point of this distribution. So the first minimum of this diffraction pattern, so to say the representative width of that diffraction peak, is given here. The 1.22 comes from the 0 point from the Bessel function, which is this sine square over square behavior, and it defines the radius of the diffraction pattern. So in the next minutes we're going to take a look at an application which is the projection of this diffraction behavior to the question of optical resolution of optical devices. So let's come to the example. The application, optical resolution. Imagine we just have a lens and then we have an object plane and an image plane. And you know that each point in the object plane will be imaged to a point in the image plane. As an example, we can look at a point P1, which you know how the construction works. You have one straight line through the center of the lens, which then intersects with the angle determined by the focal length of that lens, and that gives us the point in the image plane. As we learned before, this point is not, as in geometrical optics, of dimension 0, but it has a certain width, a limit, a diffraction limit, and this is given by this Bessel function which we learned earlier. A second point can be constructed and we can ask, where is this image? The image is of course at a different point in the image plane. And now you can see if the points come closer together, then these diffraction patterns will superimpose more efficiently, and the limit of these images will be very blur. We will not be able to separate the 2 points anymore. So we define a optical resolution as a distance of 2 points in the object plane which generate diffraction patterns where the minimum of the diffraction pattern of point 1 here is exactly in the same position as the maximum of the diffraction pattern of point 2, which would be right here. So exactly at this point we say this defines the distance at which we still can see 2 points P1 and P2 separately. In a now following little mathematical addition, we will see the analogy between this distance and the numerical aperture of a lens. As you may recall, the numerical aperture is, so to say, the opening of a lens, so the maximum angle at which the lens can take contributions from an object plane, in this case here 2 alpha max denoted. And if you now look at the mathematics of the result, you remember the minimum resolution can be now derived as the difference of these 2 maximum and minimum diffraction patterns. This is 1.22, again the Bessel factor, lambda over d times g, and g is the distance of the object plane to the lens. And now we can substitute a few values. If we approximate alpha max with the sign of alpha max, then we can define the numerical aperture, and if we plug that in, we get a combination of the numerical aperture of the lens, the wavelengths, and the minimum distance of 2 points to be resolved. So even if this formula here relating the minimum resolution with the numerical aperture and the wavelengths, as said, is pretty simple. However, you can remember it in an even easier way, that the dimension of the resolution is somewhere close to the wavelengths of the light of consideration. 0.6 can be approximated by 1. Numerical apertures usually are of the order of 1, so that we can say the resolution is in the order of the wavelengths of the light considered. After this application, I will now show you an outlook, and in this outlook we will see the difference between a diffracted classical light wave and a Gaussian beam, which will behave principally differently, digitally differently, as we will find out in a minute. So again, you have seen this picture before. In this example of diffraction, we have a homogeneous intensity distribution in the diffracting area, and the result in the far field was this Bessel function, or the Airy disk as we learned it. Now, if we change the intensity distribution at the diffraction aperture position to a Gaussian beam, we will see a different solution. What's happening is that in the far field again we will have a Gaussian beam distribution. So this distribution shows no 0 points. We have just the approximation of a diminishing electric field with large distances from the optical axis. And the important thing is that this distribution, this Gaussian beam distribution, does not change along its position at the optical axis Z. It always stays a Gaussian beam. So this is important because we will need it when we describe lasers. A plane wave being diffracted at some aperture generates 3 regions of diffraction: optical, limit, shadows, the diffraction of Fresnel, very complex interference patterns, and a rather simple far-field solution, the Fraunhofer approximation in large distances. If we look at a Gaussian beam distribution, the transformation, the diffraction of an aperture will not change the distribution of this Gaussian beam. It will stay Gaussian wherever we look at it along the optical axis all the way to infinity.